pleasure here at the Tsinghua Laboratory of Brain and Intelligence at the Tsinghua University, Professor Xiaoqin Wang, to deliver his scientific talk on how music influences the brain and our health. So Professor Xiaoqin Wang, the floor is yours.
Oh, really um, warm feeling to be here. This is my second time in Bali. I was here a year ago, and for the I study explaining the first um, bring and music workshop. This is the second one. It's a very special honor because as a scientist, to be able to explain to you what we do in science, particularly brain and music, is opportunity, is great honor. It's also a great honor, special honor, because my colleague Stanley Christie is here in the audience, and I just speechless. So I hope in next 45 minutes or so, I can share with you some basic knowledge on how the brain work to process music. Many of you, all of you listen over there. Secondly, some of the cutting edge research we're doing right now that try to understand this process. So um, many of you might know last year, 2024, Nobel Prize in given to two scientists, to many people's surprise and to many people's expectation, that the two scientists who made fundamental contribution to artificial intelligence, okay, intelligence. This is really important event in modern science because until now, computer science was never given Nobel Prize. But why they were given Nobel Prize? Because its contributions they made, the artificial system we know today, forever change how we live and work. But the reason I bring up is ask, what is next? So if you talk to scientists anywhere in the world, what will be the next big question we as scientists and engineer want to solve? The next question, in my view, many people agree, is here. What is the biological basis of intelligence? So the artificial intelligence AI system is not really intelligent. Its computer system sophisticated enough allow us to use existing knowledge to do predictions, to fittings, to help us do this and that. But it's not near close to what we all have in our brain that we consider a human intelligence. So this question was proposed 7 years ago when at Tsinghua University, we created this special institute called the Tsinghua Laboratory of Brain and Intelligence, where Professor Stanley Christie has been working with us for the last couple years together to tackle these very important questions, the biological basis of intelligence. That is, if you look at human brain in a few minutes, I will dissect some inside of this. What is that element, working circuits, that make us human being uniquely special? Okay. Now, of course, unanswered question has many practical applications. This would allow us to build human-like artificial intelligence system, eventually help us to a better life. So in our approach, one of our approach to understand the biological basis of intelligence is through the study of music. Because we believe music is a window into human intelligence. This is something very unique to us as humans, but we do not yet fully understand why it's so unique and how does our brain process this. This is what brought us to Bali, me and many of my colleagues in the audience. We just finished 2.5 days of exciting scientific symposium with the scientists, engineers, doctors and musicians. Okay, that's the question we're asking today. Okay, now why do we humans listen to music? Every year, I teach students at universities. I ask this question. I'm asking question for all of you. We all enjoy music, but why do we listen to music at all? This question, Charles Darwin actually wondered himself long ago. He said in this famous book of Descent of Man, as neither the enjoyment nor the capacity of producing musical notes are factors of the least direct use to man in reference to his ordinary habit of life. They must be ranked among the most mysterious with which he is endowed. The so-called ordinary habit of life is what we eat, drink, breathing. Without we die. But music, if we don't listen to it, we still live. I ask students every year in American universities in Beijing, why do we listen to music? This is an important question, not necessarily a philosophical question, but in our view, is a biological question. This is what the reason we study the brain. Charles Darwin also went on to write this passage in his autobiography that I just cite here, that he said if he would live his life again, he would read some poetry and then listen to some music at least once every week so that his brain will be kept alive and youthful. And at that time, he has no knowledge of brain science as we will be discussing today. No idea of music could be used as tool for medicine and therapy. But he did say that by doing so, this might enfabling the emotional parts of nature. So in short, if I give you message today, is what does music do for us? Why we have to listen to music? Because if we human have a soul, music is that a message that's touch our soul. That's why we need it beyond eating, drinking, and breathing. And we as neuroscientists are trying to understand which part of our brain actually does this operation. Now, if I show this picture to you, some of you know this picture, many don't. I ask you, is this beautiful? I think most people say it is beautiful. Now, there are many pictures I can take as this Indonesia. So I will take some pictures in this trip, and then next time when I give a talk in US, Europe, or China, I will show a picture of Bali, ask a similar question. But here's a question. This is one of the most beautiful places in China, if you have not been to. All the Chinese people knows in place called Guilin, okay, called Guilin. This is what Chinese culture consider the most beautiful scenery. Once I gave a lecture 15 years ago in Israel, Middle East. There's no river, nothing. I showed this, asked them, is this beautiful? They say it's beautiful. They've never seen this in their life because it's all desert. Okay. The question is, I use this analogy to see why we as humans see beauty. We see beauty like this. We see beauty in sunset and sunrise. This is the same question we're asking. Why is music beautiful? When we listen to music, we feel its beauty. It's not necessity we have to listen to it, but it's beauty we enjoy. Why it's beautiful? And how does the brain process music? Which is the theme of my lecture today. And then I end up my lecture by discussing how can we use music to improve our health. I think many people in the audience are interested in this. So what is music? To begin with, I had my initial training as an electrical engineer. I turned into a neuroscientist. So for any engineer, any computer scientist audience, you can immediately understand when someone play a violin. Oh, okay. When someone play a violin, general sound that you can plot in this form: frequency, time, and intensity. If you are musicians, you can further write down the notes of the music that has contents like melody, harmony, rhythm. That's music. That's going into our ear. Okay, depends how you look at it. Now, but how does our brain accept this? So if you can excuse me for a few minutes, I'm a teacher. I teach every year. I just want to share with you the basic knowledge we already know as a scientist. How does music get into our ear, get in our brain? This is it. Now, our human body has brain and has senses that allow us to live in the world. We can see things from visual system, hear from the ear, and feel from the hand, and smell from the nose. And these senses bring the outside information, if you can sit down here, into the brain, and the brain make decisions and generate memory emotions, and then tell our hand and foot to act. So if you are musicians, you can play. In a few minutes, you will see pianists play here. That's controlled by this system. So for music, this system involved is hearing that is through our ear. And I've been studying hearing for 30 plus years. Now, but what is brain like? I suspect many of you have actually never seen what a brain like. This is a picture of the brain taken from a hospital after a person pass away. Doctor take his brain, preserve it. And so this is not living brain, but it's brain real as can get it to. And what you can see here is the brain. This is the side of your brain. It's like I'm sitting here, you're looking here without my skull. You see how all the wrinkles, we call it sockets. And everything we have, every emotion we have, every love, every hate, everything we have is inside. There's about 1 kilo tissue. Okay. Now, if you analyze how this does, this is how scientists does. Now we give a color, but this color is fake. We put a color here, so you can see brain has different areas: the frontal lobe, the parietal lobe, the temporal lobe. What makes us hear music is around here. Okay. Now, modern days, engineers have developed techniques such as MRI, magnetic resonance imaging, so that you can see the brain of a live person. This is the brain of a live person. If any of you go to hospital, take a picture, you'll get it. So you can see those wrinkles, the sockets. Then scientists can use this to analyze it. Okay. Now, then let's go back to the music. If someone play an instrument here, that sound goes to my ear. How do I hear it? Well, the sound come to ear through the ear, and then go through processes, several stages, eventually reach the brain. So when we say we hear music, precisely, it's not our ear. It is our brain that hear music, okay, through the ear. Now, ear is actually a very sophisticated technique. This is everything we need to know to begin with, to know the music. So sound coming from the ear canal, generate oscillation and eardrum, and then goes into the device called cochlear. And the cochlear has vibration apparatus inside where music and other sound are generated in the signals into the brain. So if you dissect this further, then cochlear has those very carefully structured biological organ called hair cells. And these hair cells vibrate. Then music make them fire action potentials, pulses into the brain. And the brain can send a signal back to control this. So when you pay attention to a piece of music, it acts on here. Now, this is a bit technical, but inside the deep in the cochlear, there are these hair cells that goes back and forth when you hear music. Okay. If this is damaged, for example, if you go to a place where it's too loud noise, or if you have disease from genetic inheritance or other medicine, then you could lose this. Once you lose this, you will never not be able to hear. So this is the most sensitive organ in our body, allow us to listen. Once music signal goes through here, it become what we call electronic pulses. So from here, so they go to this electronic pulses literally right now in every one of you in your brain, because you're listening to my talk. There are those pulses going on, conveying my voice well into your brain right here behind the ear. Okay. Now, how does a scientist analyze this? How do we analyze it? This I just told you the process. Sound going here, eventually understand is music, piano, or violin, or other things. Well, there are three levels of analysis we conduct. Okay. First level analysis is we analyze what's acoustic features of music that brain process. Then we analyze what kind of emotional contents that music carry. Finally, we answer the question why music sounds beautiful, aesthetics. Okay. Now, one of the things that's interesting in nature create is that the cochlear, I just explained to you, that is the first apparatus of music processing, sound processing, works like a piano keyboard, literally. So if you expand the cochlear, it's like a piano keyboard. You touch any part of a cochlear, there's one sound that's producing. So let me give you a computer simulation, show you what it would be like if you have a little eye into the cochlear when it's listen to music. Can you play video, please? So this is a computer simulation based on the data scientists gathered. Show you the vibration within the cochlear when a simple tone, complex tone music. There should be some sound to see if you can produce. Okay, so this is within a cochlear. Can you play some? Okay, this is one tone, high tone, three tone. Let's work at. So when we all hear this sound within our ear, that's vibration. Okay, it's like a many keys being played. Now you can tell low frequency here, middle frequency here, is high frequency here. So this gave you straightforward view of how the piano keyboard generates sound into our ear. But it does not tell you how multiple sounds are combined and give rise to music. Individual keys does not make music. So another aspect of this is that music is not just about hearing. Everything I told you at the moment is hearing. You can feel it because music is a multi-sensory process. Play music instrument involve both auditory and tactile perception. Can you play sound? This is a video I took yesterday during gamelan performance. Really marvelous, beautiful sound. And is it finished? So anyway, what you can see here, when musicians play music, gamelan or any instrument, not only it generates sound we hear, but it also generate vibration their fingers feel. So that's why when you go to a concert hall, you're sitting there, you feel, you hear music, your body have sensors, it feels. It's different than you hear music from earphone. Now, how do human knows there's a vibration? That's because in our fingers, we have receptors that sense the vibration, such as the one shown here. When someone play violin, the finger touches the string, but underneath each finger surface, there are a number of receptors that are sensors of vibration, very sensitive vibrations. Okay, among them, for example, there's one called Pacini that is deep in their finger that can sense subtle vibrations at a very highly active during natural behavior. So for any musicians play any instrument, your somatosensory system, we call it touch, and auditory system work together. That give you the music generation process. And for the audience, If someone play music in a few minutes, the front row guest would feel that vibration directly. Now, the vibration from fingers, from a body, and the sound from the ear all eventually are integrated into the brain structure called insular. And this is a place, if you have damage, then you lose the sense of music. That's called a multisensory integration. Now, put it all together. When we go to concert hall or go to gamelan performance, we listen to music. How many places in the brain are involved? Many. I will share with you a few. Here shows a view of the brain from the right side and looking inside. Different color indicate different level of processing. Let me give you an example. For example, when you hear music being piano, violin, gamelan, that are different acoustics, is this part of the brain, green color, audio cortex, that's activated. Then when you focus on music and check it, memorize it, then it's this area in the frontal cortex that's activated. Now, sometimes when you hear music that is so touching, bring you into tears, emotion, then it's a structure down here, red color, that evokes emotion. Scientists have done a number of experiments to review it. I'll just give you two examples. They have reviewed, analyzed different parts of the brain that process to frequency, that's non-music sound. They also found that there are parts of the brain that's right behind our ear that specifically respond to music. This is the green one and the blue one. Okay. But one good news is this species area that all of us have is not unique to musicians. Whether you are musicians or non-musicians, you have the same area. This is perhaps what we're born with. This is possibly one of the human uniqueness in our brain, allow us, any of us, whether we're musician or non-musician, appreciate music. Now, the another level to understand music is understand the emotion contents in the music. Because when we listen to music, this part of the brain is activated. But when we remember music, other parts are memorized, they're activated. So my laboratory have done studies to test the emotional contents of music, of a sound. In this case, is voice. Voice, when you sing, carry emotion formation, just like music. And we found in this insular cortex, which I mentioned to earlier, that integrate different modality. Neurons there are sensitive to peripheral emotion signal. So when you listen to beautiful music or not so beautiful music, your ear does not tell. It's your brain here that tell. So that's why, as a neuroscientist, musicians often say we train our ear to learn music. Neuroscientists, perhaps after today, all of you will think it is our brain that is listening to music, but it's through the ear. Okay. Now, this is another study done by a scientist called Bob Zaturo in Canada, and which has shown that when you listen to the familiar music that make you very pleasurable, but a familiar one, these part of the brain are activated, the so-called rewarding system. So when you anticipate of very pleasurable music that give you chills, is this place, DS. When you have experience of this, is this called ventral striatum. Okay, but when you listen to, sometimes we listen to music we never hear before, but it just make us pleasurable. When you listen to novel music, then other places and there's a connection between these brain regions that is active. So it's through this experiment, this type of experiment by many scientists over 30, 40 years, we began to slowly understand each part of the brain responsible different element of music. Now, one of the things that's very important for music, that's almost to the core of what we learn and play music, is we memorize music. When you hear a familiar piece, you just need to hear 1 second, you know the rest of them. Okay? Where this memory stored, And we have conducted a study in Beijing a couple of years ago where we did the following. We asked a subject to rank 10 most familiar music. And we play 1 second, we stop. The rest, the subject recall. So that's the experiment. We let them recall in control, we let them listen the entire thing. So then by working with neurosurgeons in the hospital, sometimes the patients, they have tumors and epilepsy that need surgery. Physicians will put electrode there. Then there's a small window we can record what people's response to. This is a very rare opportunity into the human window. Okay. Then we find out that in the part of the brain that when you listen is activated here in the auditory cortex, in the frontal cortex, that when you recall, okay, and this direction of information flow is different, okay. So finally, I'm going to cover that's how do we approach the question why music is beautiful. This is one of the most interesting, the most difficult question. So I'm going to show you this video. Can you play? This is Rennie Fleming, who is a very famous opera singer. Several years ago, he volunteered himself
research coming out about the fact that music
as
has
a
been discovered
subject
to be
for
in
research
a lot
in the
of parts
National
of the
Institute
brain,
of
and therefore it engages
Health.
so much of us.
It's an exciting time in neuroscience. We're beginning to understand how the brain interacts with the environment. And music is a really important part. We're starting to learn ways in which music can influence all kinds of other aspects of one's brain function, and especially how we could use that information to use music therapeutically in an even more powerful way. This initiative aims to bring together communities that haven't necessarily gotten to know each other that well yet, the neuroscientists and the actual.
This gentleman is a former director of the United States National Institute of Health, the chief officer for entire biomedical research. He teamed up with Rennie Freeman, an artist and singer, to begin a program to study music. Until recently, people have no idea when top world-class singers sing, what's happening in their brain. So Rennie Fleming offered himself as a subject. In a moment, you will see she will lie in a scanner, sing an opera piece, and you will see what her brain looks like. This is what I just came to behind our ear, where music eventually come into. This is a world-class singer lying down in this noise machine, sing an opera so that a scientist can measure her brain response. Okay, in interest of time, I'll move on. So that's not a way to study how the music is played, because no musicians ever play music or sing in that situation. So in last year, we move on in Tsinghua University to a different new type of experiment. We study how the brain responds to music in the concert hall, not in the laboratory. This experiment we did last year with the piano master, Mr. Kong Xiangdong, who is in audience. Mr. Kong was performing a live concert improvisation, and he was wearing an infrared imaging device, which you will see this musician put on in a few minutes. Right after finish, you will see the live demonstration of that experiment. During this experiment, Mr. Kong played improvisation for 90 minutes. We record his response. Here's some of the news data we never actually publish. Just come out. Just show you what can we learn. So Mr. Kong play first improvisation, then play the memory music. Long story short, you look at this electrode in the front of his brain. So let's say, look at this one. This highest one is when he was playing memorized music. But when he improvise or waiting, response is lower. Okay. Now we went on to did another experiment with Mr. Kong that he come to Tsinghua University. He improvised in the piano, which I believe he will demonstrate in a few minutes. And a participant listen. They do the live music generation. Then we record it. Then both of them sit back to the audience, listen to the playback again. Here's a surprise. So this is pianist's brain responses during improvisation, during listening. You don't have to be scientists to notice difference. They're different. But what about a person listen? Well, this person listening to this, complete different from the pianist. If we quantify this, what you can see is that for pianist, when he was playing, his brain response blue was less than when he was listening to his song. Okay, but for the audience, for the participant, is opposite. So if you sitting next to world-class pianist listen, your brain is much more active than you go home and listen to record CDs you buy from him. That's why you should go to concert. Anyway, so move on. Did a lot more experiment. Today, we have a pleasure to bring these scientists here. These are two scientists seated right here. In fact, they wear same color of clothes, and we did experiment like this. Okay, so I'll move on. Give you one video showing in that concert. We have a celloist and pianist. Both of them wear this kind of infrared imaging. And we record brain responses. Can you play the video? This is a brain response front, right, and left from a pianist who is playing together with cello. The color indicate the activation of the brain. Red is high, blue is low. This is in real time. This is real data. What you can see is right side of the brain. This is the auditory cortex. When she listened to her partner play cello, it activated different than the left brain. This is really we show the musician of this. It's really very intriguing that many of us have never seen when a musician actively plays this music. This is one of the most beautiful music I enjoy. So if it's not my time is off, we'll sit and listen to the rest. But let's move on. Okay. Through experiment this, not only we can measure the musicians, we can measure people in the audience listening. We hope eventually we can understand how the music is perceived by human brain. So last, I'm gonna play this video to you, which you probably never seen elsewhere. All the imaging I played to you are recorded in the human body brain in a library, in a concert. The data are interesting, but they're limited. So this is image, can you play video? That will have opportunity to record direct of the brain of an experimental animal that we can observe the individual neuron. We play a music. The piece many of you might be familiar. Now, every tiny dot here represent a group of neurons. In group of neurons, in our brain, we have millions of them. Okay, and what you can tell is a different activation in different parts of our brain lights up when different music come and go, percussions, string music. So if you fly United Airlines enough, this is beginning sound for United Airlines that you use. Okay, so let me finish by saying a few words about, in addition to all the basic research, what can society benefit from this? After all, direct benefits is something we call music therapy. So several years ago, National Institute of Health in the United States organized scientists to discuss this question. That's not trivial. We all know music can change, get you moving, lift your mood, and even help you recall memory. But can it help your health? This needed rigorous scientific study. We and others are working on this. Now, what kind of things music can do to improve health? Well, give you an example of music therapy for neurological disorders. For example, aging, Alzheimer's disease, Parkinson's, stroke, autism. All of this could potentially benefit from music therapy that I listed here. And this is a theme of a workshop we have here this year, perhaps in coming year, okay? So I'm gonna skip this. Finally, I'm gonna show this. This video shows a music therapy help children with autism, played by Professor Zhang Mengyi. She's a musician and a scientist. She's come from singing conservative music. So these kids are special kids. Normally, they cannot function in a proper social way. As you all know, this is autism kids. But Ms. Zhang and her parents taught these kids from the ground up, learning how to play instrument. Now we see how they perform. This is a very really inspiring example showing musicians and scientists can bring music into the benefits of the society. And Ms. Zhang will play with you the instrument that she played in there. Okay, so with that, I'll conclude my talk here. Thank you, and I hope this share with somebody. Thank you.
Thank you, thank you. Thank you, Professor Xiaoqin Wang. What a thought-provoking talk. Now